Good afternoon. This is a mini lecture to support homework 7 on geospatial energy levels. We're going to talk about the space shuttle launch process, and then I'm going to talk about the value of G way out on orbit, where the space shuttle used to orbit. And then we'll talk about gravitational potential energy, total mechanical energy, and kinetic energy levels out on orbit and at other places as a way of getting you started with your written homework 7. So let's take a look at the specs here. First of all, the Space Shuttle Launch System, the STS, a system at liftoff. So that's the external liquid fuel tank, and then the 2 solid rocket boosters, plus the shuttle itself and all of its payload and crew, about 2,000 metric tons. That's 2 million kilograms. That's a lot of mass. So the weight force is going to be about 20 million newtons downward. So the rocket engines have to produce a little bit more than that, or a lot more, if you want to start accelerating upwards. So it's, that's what you want to do. And we can figure out the F equals ma, or we can estimate it. If we look at the basic time and space measurements of the launch process. All right, so if you look at the launch tower, which NASA calls the Fixed Service Structure, FSS, it's about 75 meters tall. All right, and you look on YouTube, at shuttle launches, it takes a shuttle about 4 seconds from when it starts moving from liftoff to clear that 75-meter launch tower, and it's doing it from rest. Right, so that lets you use 1/2 AT squared to figure out the acceleration. So you do that, and the average launch acceleration is approximately 9.4 meters per second squared. Now that's a kind of a big, it's an overestimate, as I'll mention in a second. But you can figure out from that, what the upward thrust has to be to achieve that 9.4. So you have all your 20 million newtons to cancel the weight force, and then the ma of your upward acceleration, the mass of the spacecraft, times 9.4 meters per second squared. So that's about 40 million, 39 million, 40 million newtons of thrust developed by those engines. And just a small caveat, this is a kind of an overestimate. It's very loose because the STS loses tons of fuel per second. So that first 4 seconds from liftoff to clearing the launch tower, it's blazing out tons and tons of rocket fuel. Right? So the mass is not the same. So the mass at the top of the launch tower is going to be a lot less than 2 million kilograms. All right. So this is kind of an overestimate, but it gives you an idea of what we're trying to deal with here. And basically, we're trying to power the weight force. Now, W equals mg, here at the surface of the Earth, lovely, we use negative 9.8 meters per second squared from the top of Mount Everest down to the bottom of the Marianas Trench. But what about up here, up on orbit? Now, this is low Earth orbit. It's high, but it's not as high as satellites go. So the shuttle and space station, typical altitude is about 400 kilometers. And what we want to try to figure out is the value of G up there, because it's going to be smaller. And what that means is that, if you go meter by meter, if you're going downwards, you're getting more kinetic energy. But you're not getting as much because the value of G up there is smaller than it is down here on the Earth. You're still getting kinetic energy, but not quite as quickly. Now let's double check. Mount Everest, 9 kilometers tall, good. But how do we figure out G up at low Earth orbit? Well, the way that you do it is you use the law of universal gravitation. Now, that's your W equals mg. And here at the surface of the Earth, R is about 6371 kilometers. So, you just plug that in here and you get 9.8. Now, about this particular formula, that's the universal gravitation force law in the middle, and then good old mg over there on the right. The nice thing is you can cancel out, if you want to figure out g, you can cancel out the mass of your spacecraft or your mass of your, whatever the object is. And g is equal to gravitational constant, capital G, times the mass of the Earth times the square of the distance from the center of the Earth. So if you're at sea level, R is 6371 kilometers approximately. The Earth's not a perfect sphere, but we'll assume it's a perfect sphere of 6371 kilometers for this exercise. Now, at shuttle orbit, you're up at 400 kilometers above sea level, low Earth orbit. So you're talking R 6771. All right. And so what that means is your denominator, R squared, is going to be larger. And G up there is going to be smaller. Now, let's give it a different symbol. So let's say that out on orbit, the acceleration symbol is G prime, not G. Right? So the ratio of G at the surface of the Earth to G prime out on orbit, it's actually dependent on the two R squared values. 6371 kilometers quantity squared and 6771 kilometers quantity squared. Now, the way, you stack them up, here are the two, here's the ratio, G over G prime. And you see, GM over R squared for the numerator and also for the denominator. And you can just go ahead and cancel GM from the numerators of each. They cancel. But the distances don't cancel. And your denominator has a denominator, 6771,000 meters quantity squared. By the way, that's 6771 kilometers converted to meters, and it's quantity squared. And that's the denominator of the denominator, so that goes into the numerator in the simplified form of this. And that works out to about 1.130 to 4 significant figures. So G is about 1.13 times larger than G prime out on orbit. In other words, G over G prime is 1.130. And what that means is that, do a little cross multiplication. G prime is equal to G divided by 1.130. And so that works out to 8.7 meters per second squared for the value of G prime out on orbit. Now we're going to put a minus sign on that in a second. So let's just review. From sea level up to about 9 kilometers, GPE, delta GPE minus mg delta y, nice, works perfectly. Negative 9.8 meters per second squared, lovely. And it works all the way down to the bottom of the Marianas Trench. Although, it's kind of hard to do gravity experiments down there if you're in a little teeny submarine. But yeah, that gives you a delta Y range of about 20 kilometers. Right? So the 20 kilometers, above and below, above, so about 9 above, 11 below sea level. It's 20 kilometers. And we're going to use that distance range in some of our diagrams here. And here's a question that you can ask yourself. How much change in the GPE does the space shuttle lose to kinetic energy as it descends from low Earth orbit at 6771 kilometers down 20 kilometers to 6751, right? So that's that would be a kosher estimate of delta GPE and delta KE for the space shuttle. In other words, the first 20 kilometers down that it goes when it starts to deorbit. And it's in the landing process. All right, so let's take a look at a GPE diagram here. Vertical scales GPE. I haven't put any joules in there, but I'll do that in a minute. But what I have done is put an arrow down here in the first 20 kilometers to represent the value of G here on terra firma, negative 9.8 meters per second squared. And up here, I've done, this is out at Earth orbit, 400 kilometers. Right, so here's another arrow. Now, the tilt of these arrows up here on Earth orbit's negative 8.7 meters per second squared. They look pretty much the same, but they're not. So the tilt of the arrows, I did it really carefully. It represents the change in the GPE per meter. Now, that has a physical meaning, but for right now, I just want to explain the tilt of these two arrows. All right, and this is kind of a rough diagram of what the gravitational field is doing. So up here, you have a relatively slow roll. You're accelerating downward, but it's only 8.7 meters per second squared. Down in the first 20 kilometers, it's a little bit faster. Right? Now, I want to do a tilt check just to show you that these two vectors, these two arrows to represent the strength of the gravitational field, they're not the same. They look pretty close, but they're not. So let's put in a red line segment. There it is. And that's parallel to the black arrow out at low Earth orbit, 400 kilometers. Now let me move that down here to the black arrow down at terra firma. And you can see that they don't have exactly the same tilt. Now, another way to do that is with a right triangle that tilts the same as the black arrow out on low Earth orbit. So here it is, this pink triangle. And you can see it's got the same slope as the black arrow at low Earth orbit, 400 kilometers. But now if you look down at the bottom left, it's definitely not tilting at the same angle. It doesn't get to that black arrow. So they're not those two arrows, those two black arrows, they're not parallel, right? They're not tilted at the same tilt angle. Right? Now let's do another triangle. This one, the gray triangle, yeah, this one's lined up with the arrow down at the first 20 kilometers. But it, you look up here, it's definitely missing. It's overshooting the black arrow up there at low Earth orbit, 400 kilometers. So it's kind of bodacious. Now, that means that if we want to have a line, not just two arrows, but a line, it has to be parallel to both arrows where the arrows are, right? Now, they're different tilts. And this, I really carefully did this with a spreadsheet, this particular blue dotted line. And let me move it in so you can see. Oops. I got to go through this again. Here we go. All right. Tilt check. Yeah, we don't have any good. They look close, but here's the gray one. Let's move that out of there. All right. And here's this blue dashed line. Now let me move it in a little closer. And you can see now it overlaps both arrows pretty well. But since those two arrows are not the same tilt, what it means is you've got a really gentle curve at this scale. So if you graph up the first 400 kilometers of the GPE function, it looks straight line, but it's not. It's actually curving just a little bit. Right, now we're going to back up and look at a lot more kilometers of altitude here in a second. And what we're going to use is this function. This is the actual potential energy function for, the mass of a spacecraft orbiting planet Earth. So there's a minus sign out in front, gravitational constant G, the mass of the spacecraft, and then the mass of the Earth, M, with a little circle with a plus sign in the middle of it, divided by R. Now that's not R squared, it's R. Right? If it was divided by R squared, it'd be a force. This is an energy, potential energy, and it's negative. Right? Now, here's that curve. And what I've done here is a lot more altitude. Now down here in close, this little solid blue line segment is where we just, the picture that we just did. That's sea level out to 400 kilometers of altitude, right? So that's sea level out to 67, 71 kilometers. And this horizontal scale is now in meters. So you can see that 6.25 million meters is 6,250 uh, kilometers. And so that's that first vertical reference graph paper line. And the curve starts just a little bit above that, in other words, the surface of the Earth. Anyway, so the graph of sea level up to 400 kilometers that we had on the previous slide, it's this little blue line segment here. Now, if you follow it all the way out here, at a good distance, for instance, right out here, geosynchronous orbits are out here, about 6.6 Earth radii. You can see that the potential energy function curves nicely. And that little blue line segment, it looks straight. It's not straight, but it looks pretty straight to the naked eye. But if you look on a larger scale out to, 6.6 Earth radii, you can definitely see the curve of this function. Now, a side note I'd like to bring up to you is the 0 point. In class, we talk about, basketballs and stuff, and the 0 point is the gym floor and whatnot. And the 0 point is important to define. But in this context, we usually make the 0 point, the GPE 0 point location, be at infinity. And you can see that from this curve. It's curving upward, and if I keep graphing it up, it'll get closer and closer to the very top of the graph paper, which is 0 joules of potential energy. All right, so way out there to the right, the function u of r goes to 0 as r goes to infinity. So that's kind of like an infinite limit type of a deal. All right, now we're going to bear that in mind when we do our homework calculation. I mean, it's not like you got to do any calculus, just know where the 0 point is. Now let's take a look at the steepness again of this baby. And this is the curve, and we looked at the steepness of the low Earth orbit bit down there in the solid blue line segment. Let's take a look at this one up here. The steepness, in geometry class, is rise over run, and you got a line segment, you get your right triangle, you rise over your run, ding, you got your slope. But in physics class, it has, the rise over the run has a physical meaning. It's delta U over delta R. And so you've got joules of potential energy, and in fact, negative joules of potential energy in the numerator and meters in the denominator. Right now, that has a physical meaning that I want to talk about. So let's kind of unpeel this. Okay, so delta U over delta R, that's going to be in the numerator joules, kilogram meter squared per second squared, and down the denominator it's going to be meters. All right, and so you cancel a factor of meters, and what that leaves is kilogram meter per second squared. Now ask yourself, what is that? Think. Kilogram meter per second squared. What is that? If you think about it, that's just a good old Newton. So the steepness of that blue curve represents it's an energy gradient, delta U over delta R, and it represents the strength of the gravitational field. So where it's steep, you have a relatively strong gravitational field, in other words, closer to the surface of the Earth. Where it's flattening out, it's you still got some gravitational newtons out there, but not as many. It's not as strong because it's further away from the surface and further away from the center of the Earth. Okay, so um, that's one thing to keep in mind when you're looking at this curve and thinking about your homework. Now, another thing I want to go over with you is the energy situation. Now, we know that the total mechanical energy is equal to potential plus kinetic. So in this case, it's gravitational potential energy plus kinetic energy. Now, the blue line is the potential energy. The total mechanical energy is going to be a constant, for all elevations, for all altitudes. That means it's going to be a horizontal line segment if you were to draw it in. So let's draw it in. And I just chose this one, negative 3.5 times 10 to the 13 joules, because that's one of the lines of the graph paper here. So that's an orange. So let's say that we have a spacecraft that has or the shuttle has a total mechanical energy of negative 3.5 times 10 to the 13 joules based on 0 being at infinity. Right now, if that's the case, the difference between whatever the blue line is and the orange line is your kinetic energy. So think of it this way: kinetic energy is E minus GPE. Okay. So what that means is, right here, there's your, that vertical line represents at that altitude how much kinetic energy. Now, if you go up in altitude, like right here, you've got a little bit less kinetic energy, and you can calculate it. You figure out your altitude. This one looks like it's about. Let's see, that's going to be about 12, maybe 13,000 kilometers. You go a little further, you get a little bit less, and eventually you're out here at this level. And you have, you're at apogee. You don't go any further. That's as far as you can go at this energy, negative 3.5 times 10 to the 13 joules. So that's your apogee, and that's where your GPE is maximum. Where GPE is maximum, kinetic energy is a minimum. All right. Now the thing about this is all radial. All right. And there's also angular kinetic energy that we haven't factored in. And that actually changes the shape of this graph just a little bit. But, so I can't put in perigee on this graph. I can put in apogee. Right? So whatever your, if you know what your total mechanical energy is, and then you calculate your potential energy, you can figure out kinetic energy. Just like the basketball problem. You figure out potential energy at any level, then you figure out your kinetic energy and figure out your downwards, your free fall speed at whatever elevation you want. All right. Now, I calculated this out. This distance, or from the center of Earth, is 22,871 kilometers approximately. All right, so that's it's about halfway between geosynchronous and low Earth orbit. So we got satellites out that far. Various kinds of satellites and stuff. And spacecrafts going to the moon or different planets, they go past that point. Now, I want to give you a little bit of detailed information concerning the actual homework assignment. So let's take a look at that now, and this will be our last slide. First thing we're going to do is calculate the gravitational potential energy at the surface of the Earth, 6371,000 meters. And we're going to give that the symbol U surf, U subscript surf. And we're going to assume that the 0 point of U of R is at infinity, as we mentioned before, so we use the same kind of curve. And so your GPE is going to be a number deep in the negatives, and you'll be able to calculate it. But you got to look up the value of G. It shouldn't be too hard. And the mass of the Earth, that also shouldn't be that hard. All right? Now, what we're going to try to figure out is escape velocity and the escape kinetic energy. Now, to escape the gravitational pull of Earth, you have to have that much kinetic energy. So whatever you calculate for GPE, you have to have at least that much or more kinetic energy, so maybe an extra joule or so at launch, so that the total mechanical energy is non-negative. All right, now this is pretty rough. I mean, it doesn't develop its max kinetic energy till, it's up at altitude. But let's assume that it's like a bullet from a gun. As soon as you hit the trigger, in a fraction of a second, the bullet's got its total its max kinetic energy. So we'll kind of think of the space shuttle that way. Now, if the total mechanical energy is non-negative, that means it could be zero or it could be positive. If it's zero, then that means you reach infinity, but at a very slow rate, or what we would say asymptotically reach infinity. So you're getting further and further out, as far out as you want to go, but you're losing speed. So you're down to like a millimeter per second, and then a nanometer per second, and on down. Now, it's kind of a theoretical limit. So the other condition is, what if you have more than zero? Your orange line is up above zero. Well, then you reach infinity with a bit of kinetic energy. Okay, and we have systems that do that. For instance, Voyager 1, I just figured out its kinetic energy and stuff. And it's got a total mechanical energy of about 106 gigajoules. So that's 106 billion joules of total mechanical energy. And most of that's kinetic energy. And it's blazing out of the solar system. It's pretty impressive, actually. All right. But if you have, on the other hand, if you have a negative value for total mechanical energy, something less than zero, which, the orange line on the previous slide was, below zero was negative. That means you have a bound orbit, right? So zero is unbound and positive is unbound if you're talking about total mechanical energy. All right. So what we're going to do is calculate E equals zero, the minimum escape kinetic energy. If you have this much, when you blast off from Kennedy Space Center, you're going to escape the pull of the Earth asymptotically slowly. If you have more than this, you'll have even more kinetic energy as you go further and further away from the Earth. All right, so calculate that, and then from that calculate the escape velocity for the fully loaded STS. Now, again, I'm going to just give you the proviso that the fully loaded STS does not go to orbit. I mean, it jettisons everything except for the space shuttle. But we'll just assume that the entire kit and caboodle is going out there to infinity. All right. And the last thing I want you to do in your homework is kind of an everyday comparison of your minimum escape kinetic energy to some everyday quantity of energy. So, you go to, the hardware store and get some propane. They're going to give you 15 pounds of propane, roughly. And that's 342 billion joules of energy. Seems like a lot, right? Okay, but you're going to figure out how much kinetic energy you need to develop to get to infinity to escape the gravitational pull of the Earth. So your question is, and this is the last calculation you make, how many of those 15-pound tanks do you have to order from, Strickland Propane for the STS to get to escape velocity? So you're going to get kinetic, you're going to get GPE, you're going to get KE, escape velocity, and then you're going to get your, how many tanks to order of propane. That's going to be kind of like a little check on what we're doing. And it's going to be a big number of propane tanks, because just think of those, the solid rocket boosters. have a huge amount of joules per ounce of solid rocket fuel. That's why they use them. And then the liquid fuel is also loaded with joules per ounce, and you got a huge tank of it. So, I mean, there's a lot of, there's a lot of joules to burn, and so we're going to be comparing, the actual rocket design, liquid fuel, solid fuel, to the propane system, 15 pounds of propane per tank. All right, so that's homework 7 background, and if you have questions about it after you start, post a question in discussions, and that'll be good. We'll talk about it in discussions.